Hello, everyone. Thank you for giving me the opportunity of being with you today. My name is José Cafiero. I'm from Argentina. I hold a degree in economics from the University of Buenos Aires and a master's degree in international affairs from Columbia University in New York. I used to teach microeconomics and regional economic integration at the University of Buenos Aires. I used to teach international trade at the University of Museo Social Argentino. And I used to teach econometrics at the postgraduate level at the National University of La Matanza. In this lecture, we are going to talk about basic regression analysis with time series data. Let's begin with some comments about the nature of time series data. The analysis of data has been observed at different points in time, or time series data, presents new and unique challenges for statistical modeling and inference. Of paramount importance is the correlation introduced by using the sampling of adjacent points in time. This fact disputes the validity of statistical methods dependent on the assumption that these observations are independent and identically distributed. So far, we have mostly worked with cross-sectional data, which represent random outcomes in the same period of time. Time series data, on the other hand, characterizes a temporal order such world GDP from 1919 onwards, for example, under the implicit assumption that past events can affect future ones. What we observe are realizations of a stochastic process. In this sense, if certain conditions in the past have been different, we would observe different values of the same time series. Unlike cross-sectional data, which suppose that data points are independent, time series data precisely depends on time and may exhibit trends and other time-related patterns such as seasonal, cyclical, or residual. At this particular point, let me talk to you about another kind of data that is called panel data. It's a type of data that is collected by observing particular variables over a period of time at a regular frequency. It combines time series with cross-sectional data, increasing the quantity and quality of data at our disposal. Now, we are going to talk about the static model. Suppose we have data in a time series format, obviously, relating world total imports at time t, y sub t, with world gross domestic product also at time t, x sub t. As usual, we can model this relationship in the following way that you can observe in equation 1, where remember that u sub t is a sequence of errors or disturbances that represent all unobserved random factors that can affect y sub t. In this case, we are modeling a contemporaneous relationship, and a change in xt is associated with an immediate change in y sub t, being the change u sub t equal to 0. There is also the possibility that the dependent or response variable y sub t might be affected by other contemporaneous planetary variables. Suppose that y sub t represents imports from country I from country J at time t. And that date can be related not only with I GDP, but also with the real bilateral exchange rate between I and J, Z sub t, at time t. Then you can have an equation like equation 2. Now we are going to talk about a little bit about the finite distributed lag model. Remember that taking into account that the explanatory variables can affect or can be associated with the response or dependent variable with a lag. In general, we can explicit this relationship with equation 3. You see the y sub t is not only related with x sub t, but also related with lagged values of x sub t. This is a finite distributed lag model of order q because we go to until the lag number q. Given a permanent increase in x, the so-called log-wrong propensity or log-wrong multiplier is the sum of the beta coefficients. We can model 3 with several lag explanatory variables too. In our example for export from country J to country I can be related not only with GDP of this year, but with GDP of former years, of past years, and with the trajectory of the bilateral exchange rate between the two countries. Well, just discuss a little bit the finite sample properties of ordinary least squares under classical assumptions. If we use the technique of ordinary least squares that you already saw in the case of cross-sectional data, to estimate the parameters implicit in equation 1, 2, and 3, and many others of the same family, we must consider its finite sample properties. When we studied, let me tell you again, this issue in the case of cross-sectional data, it was shown that OLS estimators were the best linear unbiased estimators, or characterized by the acronym BLUE. In this lecture, we are going to show that this is also true for the case of time series data. For that matter, we are going to use 5 classical assumptions. Assumption number 1. The stochastic process y sub t x sub t1 till x sub t k minus 1 for k minus 1 explanatory variables and with t equal 1, 2 till n periods of time follows a linear model. Remember that we used to talk about that the equation, the data that emerged for equation 4 comes from a data generative process, random data generative process that we observe one of the realizations of that process. And this is taken in account in the data that appears in equation 4. That's the general idea that is behind the formula or the formalization of equation 4. But we assume in assumption number 1 that this model is linear in the parameters, in the betas, not in the variables. The variable can be of any sort. Okay, they can be square, they can be logarithms, they can be multiply one variable by the other in order to look for interaction. You can do whatever you want in that respect, but the betas are always linear. Okay, the relationship between the betas and the explanatory variable, is always linear. That's why this is a linear model. Well, and in order to continue with the lecture, let me simplify a little bit the notation and name a matrix X with n rows that represent the time periods and k columns representing all the explanatory variables plus the constant. Then we can present the equation 4 in the following slide. Well, as you can see in equation 5, there is a syntactic way to represent equation 4, and we have y is an n by 1 vector containing the n observations over time of the response variable. The matrix X is an n by k matrix with a column of ones that represent the constant, and the other columns containing the n observation over time of the explanatory variables. The vector beta is a k by 1 vector that contains the coefficient to be estimated, and U is an n by 1 vector representing the error term over time. Assumption number 2. For each time period t, the expected value of the error U sub t, given the explanatory variables for all time periods, has to be 0. So the disturbance term is not correlated with each explanatory variable in any time period. They're independent. This assumption, named strict exogeneity, is much more stronger than the one we saw in the case of cross-sectional data. There, the explanatory variables must be only contemporaneous exogenous, because random sample and the absence of temporal dependencies make these stricter conditions unnecessary. Here, the explanatory variables has to be strictly exogenous because random sampling is almost never appropriate. Bear in mind that there are no restrictions on correlation across time series in the explanatory variables. Strict exogeneity can be violated by, among other things, omitted variables in the model, variable measurement or errors, as well as other subtle facts can render this assumption unrealistic. We have to check for that. In some cases, the proper use of finite distributed lag models might be the right approach. Assumption number 3. No explanatory variable is a perfect combination of the others, nor is it a constant. This means that X, that is also called the design matrix, has full column rank. All columns of the matrix X are independent. As we are going to see later, this assumption ensures not only the invertibility of the matrix X transpose X, but also that it's positive definite. In the presence of multicollinearity, bear in mind that these methods tend to be very imprecise, and they exhibit high variance, and this is a serious drawback for the whole estimation process. At this stage, it will be very useful to show you how to get the OLS estimator. And this is going to be done by minimizing the sum of the square of the residuals with respect to beta. Using 5, we can get an expression from the sum of square residuals in a matricial form, as you see in the first equality of the slide. Then there you apply rules regarding transpose matrix and distribution in operation with matrices. If you have any doubt, please let me know, and I can be more explicit about that. Then we are going to have the second expression, and that expression we have to take the first partial derivative with respect to beta expressed there in a matricial form. We have a gradient, what is called gradient, expressed there. And we have to equate the first partial derivative of the sum square residual with respect to beta to 0. This is, as you may know, is a necessary condition for a maximum or a minimum. Then what we have to do is to solve this equation in order to get the value of beta that equates the expression to 0. But first, we have to know if there exists a solution, if there is an inverse for X transpose X. And we know for assumption number 3, by assumption number 3, that the inverse exists. So we have a solution for beta. Next, what we have to do is to check if we are in the presence of a maximum or a minimum. We take again the partial derivative, the second partial derivative of the sum of square residuals with respect to beta, and we know that that expression is positive definite. Therefore, we are in the presence of a minimum. This is the classical solution for getting the OLS estimator. There are another techniques like maximum likelihood estimator or nowadays gradient descent that can give you the same results. Well, we have shown that the OLS estimator that minimizes the sum of the square of the residuals is like equation 6. Beta hat equals x transpose x inverse x transpose y. We are going to show that this estimator is linear and unbiased. Linearity in y can be directly be seen from equation number 6. And also, if we replace in equation number 6 y by its expression in equation number 5, we are going to have the equation number 7a. And in that equation, we show again that beta hat is not only linear in y, but also linear in u. And as such, is going to inherit all the probability distribution of u. Lack of bias can be shown practically in the same way. We replace y in 6 by 5 again and take expectations. So the expected value of beta hat is going to be as the one that we show in equation number 7b. But if you remember, by assumption number 2, the error term is independent of x. So the last term in 7b becomes 0. Why? Because the expected value of the error term is 0. So we just demonstrate that the expected value of beta hat equals beta. So the OLS estimator is unbiased. Now, well, as we talk about the expected value of beta hat, let's talk about the variance of the OLS estimators. We have to make a new assumption number 4, that says that conditional on x, so x can be stochastic or non-stochastic, the variance of ut is the same for all t. This property is called homoscedasticity of the error term. It means that sigma squared, that is the variance of the error term, does not depend on x. In other words, the unobservables that constitute u and affect y have a constant variance over time. Continuing with the analysis of the variance of the OLS estimators, we now must pose another assumption number 5, that said that conditional on x, the errors of two time periods are uncorrelated. No serial correlation among errors. That's what this assumption specifies. And it says that period t does not convey information about the value of y in period s through the work of ut. When this condition is violated, errors are serially correlated. And this is highly likely when we use time series data. No, it's not the same as in cross-sectional data, but in both cases, the fact of the matter is that we must always check for serial correlation. Generally speaking, serial correlated errors indicate that the model is misspecified. So we have to change the model in order to get errors that are not serially correlated. Well, now we are going to determine the variance of the OLS estimator. And the first case from non-stochastic regressors. If you remember equations 7a and 7b, we show you that the expected value of the OLS estimator beta hat equals beta because it's unbiased, and beta hat minus beta equal to the expression x transpose x inverse x transpose u. If we want to get the variance, what we have to do is to take the square of that expression expressed in matricial form. So, and then the expectation. So we have the expectation of x transpose x inverse x transpose u times u transpose x transpose x inverse. But the important term in that equality is how we solve u times u transpose. And if you remember that we are under the assumption of constant variance and no series correlation, then u times transpose u equals sigma squared, that is the variance of the error term, times the identity matrix. So that leads us to the last expression, the expression number 8, where the variance of beta hat equals sigma squared, the variance of the u term, times x transpose x inverse. Well, we are now in position to prove the famous Gauss-Markov theorem that basically says that under assumption A1 to A5, the ordinary least square estimator is the minimum variance linear unbiased estimator of beta, blue. The minimum variance property can be verified in the following way. Let's consider any other linear and unbiased estimator like b hat and equals c times y. Then we already said that d hat is a linear and unbiased. So if it is unbiased, then the expected value of theta hat must equals beta. And b hat equals, if we replace in 9 y by its expression in equation number 5, is equals to the expected value of c times x times beta plus c times u. And if we take a presentation of that equation and apply mainly the assumption number 2, we have that the whole equation equals to beta, but under one condition, that c times x must be the identity matrix. Otherwise, we cannot affirm that the expected value of theta hat equals beta. Then, using the same method as we use in order to determine equation number 8, we can prove that the variance of d hat equals sigma squared times c times c transpose. You can derive by yourself that expression. If you have any problem, just let me know, but it's a very good exercise in order to be familiarized with all these matrices and equations. Well, now we are going to define a value for C. Let C be any other matrix like the one that we see in the last equation or equality in this slide. C equals D, that can be any matrix, any other matrix, plus x transpose x inverse x transpose. Then continuing what we wrote in the last line of the last slide, now the variance of d hat equals the expression in the first equality of this slide. Sigma squared, square brackets, d plus x transpose x inverse x transpose times d plus x transpose x inverse x transpose transpose. So Cx, as we saw in the last slide, is equal to the identity matrix. But Cx equals dx plus x transpose x inverse x transpose x. And that means that dx plus the identity matrix has to be equal to the identity matrix by 10. So dx has to be equals to 0. Dx vanishes. So in order to write an expression for the variance of d hat, we expand the first equality with the distribution properties and the distribution with transpose matrices, and we have the expression that you can see in the third equality in this slide. But as we prove in the second line of this slide, d times x vanishes. So x transport d transpose vanishes too. Then the equation that we see in the third line is going to be represented by the equation that we see in the fourth line, where we just get rid of x transport d transport or d times x. And so we have the equation number 11 that shows that the variance of d hat equals sigma square open brackets d times d transport plus x transport x inverse. Therefore, the covariance of d hat is equal to the covariance of b hat plus a non-negative definite matrix. So always is going to be greater than this covariance. So we have shown that the all LS estimator is the minimum variance estimator, is the best linear unbiased estimator. Well, all demonstrations has been done for non-stochastic explanatory variables so far. So let's see what happened with stochastic regressors. Assumption A1 to A5 are expressed for both stochastic and non-stochastic explanatory variables. Usually, the explanatory variables are drawn from some probability distribution. In this case, the statistical properties of beta hat are obtained conditioned on X, as was mentioned earlier. Then the conditional results come from averaging or integrating over the conditional distribution. For example, in the case of unbiasedness, we condition on an arbitrary X, and then we average over all X to obtain the unconditional result using the law of iterated expectations. So, just go to prove unbiasedness of the OLS estimator for the case of stochastic explanatory variables or stochastic regressors. If you use equation 7a and take expectation and condition on X, we get the expression that is in the first equality of this slide. The expectation of beta hat given X equals beta plus X transpose X inverse X transpose, and then the expectation of U given X. But this expression, because of A2, is 0. So the expected value of beta given X equals beta. Then we have to prove that this is for the expected value of beta hat for any X. So we take the law of iterated expectation, and we say that the expected value of beta equals the expected value respect of any X of the expected value of beta hat given X. And this is again equals to beta plus the expected value for any X of the expression that is in the square brackets. That is X transpose X inverse X transpose, and then the expected value of U given X again. by assumption number 2 is equal to 0. So all the expression in the square brackets equal to 0, and then the expected value of beta hat equals beta. So the OLS estimator is unbiased, conditional, and unconditional as well. Now, let's analyze what happened with the variance with stochastic regressors, I'm sorry. We have shown in equation 8 that the variance of beta hat given x equals sigma squared, the variance of the error term, times the matrix x transpose x inverse. The variance of beta hat for the case of stochastic explanatory variables or regressors equals the variance of the conditional mean plus the expected variance around the conditional mean. Well, regarding the last equation, we see that the first term of the last equation is 0, is the variance of a constant, beta. And the second term is expressed in equation number 12. So the variance of unconditional variance of beta hat, the OLS estimator, can be obtained taking into account the average values of the matrix X. But as we already shown, the OLS estimator is the estimator with minimum variance in the class of linear and unbiased estimator. So the variance of beta hat given X is going to be less than the variance of any other estimator like D hat given X for any X. So if it holds for any X, it holds for 12, that is for the average values of X. Thus, the Gauss-Markov theorems hold for stochastics and non-stochastic regressors as well. Well, let's talk now about the probability distribution of beta hat. For that matter, we are going to use another assumption number 6, that says that the errors or disturbances are normally distributed with zero mean and constant bias, and you can see in the first expression of this slide. We have shown also that beta hat is a linear function of the error term and unbiased. Then beta hat given X is going to be normally distributed with mean beta and variance equal to sigma squared times X transpose X inverse. So if we are going to test hypotheses about beta or construct confidence intervals, we need to estimate the population parameter sigma squared, which is unknown. Well, so we have the following problem. Just take one element of the OLS estimator, beta hat. Beta hat sub t minus beta sub t divided by the product of sigma times the square root of the value located at the row number 2, t, and column number t of the X transpose X inverse matrix. That expression is going to be distributed as a normal with media 0 and variance equals to 1. Since the expected value of ut is 0, sigma squared is the expected value of ut squared, and then the residuals can be used in order to estimate sigma squared. So if we use the equation number 6, we can ascertain that the residuals can be expressed as in the first equality that you see in this slide. And there you can see that U hat equals a matrix M times Y. And you can see the derivation of matrix M in this first equality. Now, if we replace Y by its expression in equation number 5, we are going to have the second equality that we see in this slide. But as you can see and you can do by your own, M times X equals 0. Then U hat equals M times mu, U. Then I want to take the square of the residuals. the sum of squares of the residuals, is going to be equals to U transport M times U. Why? Because M is a symmetric idempotent matrix, and for that matter, M squared equals to M, and that's why we see in equation number 13. Then, if we take the expected value of U hat transport U hat given X is going to be equals to the expected value of U transport M times mu U given X. And this is a scalar. And a scalar is equal to its trace. And a trace, remember, is the sum of the elements of a principal diagonal of the matrix. So using the properties of cyclic permutation regarding traces, we have the expression that we have shown you in the last equation of this slide, that the expectation of the sum of square residuals for any x equals the expectation of the trace of the matrix M times the vector U times the vector U transport given X. So, as M is fixed and a function of X, let's apply the expectation to the random part of the last equality. And the random part is U times U transport given X. And if you remember, by the assumption of constant variance and no error autocorrelation, that expression equals sigma squares times the identity matrix. So we are left with the expression sigma squared times the trace of M. Now, the trace of M and idempotent matrix equals the trace of the operation that you see in the last parenthesis of the first equality. And applying again cyclic permutation, we are left with the expression that all this equation equals sigma squared times the trace of the identity matrix of dimension n minus the trace of an identity matrix of the dimension k. Remember that the trace is the sum of the elements of the principal diagonal of the matrix. So this expression equals sigma times n minus k, as we pose in the second equation. So the estimated value of the sum of square residuals for a given x equals sigma squared times n minus k. Then, unbiased, conditional and unconditional estimator of sigma squared is s squared in equation 14a, that equals U hat transport U divided n minus k. And if we take the expectation, if we take the unconditional expectation of s squared, is going to be equals to sigma squared as we pose in equation number 14b. Then the estimate variance of beta hat will be s squared times x transpose x inverse. And the square root of the tth diagonal element of that matrix is called the standard error of the estimator beta hat sub t. Well, then again, we have the expression in the first line of this slide, and as we were talking, is distributed as a normal with media 0 and variance equal to 1, but we don't know sigma squared. But Now we know that we can use S squared instead of sigma squared, and using equations 13 and 14a, we can say that the sum of square residuals divided by sigma squares equals u divided by sigma transport times m times u divided by sigma. And this is an idempotent quadratic form in a standard normal vector u divided by sigma. And as such, it has a chi-square distribution with rank m, trace m equals to n minus k degrees of freedom. We need to show now, in order to proceed, that this term is independent of the term beta hat minus beta divided by the square root of sigma squared. And as you may remember, this expression equals x transpose x inverse x transpose times now u divided by sigma. But as you can prove it very easily, x transpose x inverse x transpose times m equals 0. And this is a sufficient condition for independence. Well, what we have shown is that the vector of residuals is independent of the vector of fitted values. The covariance is 0, and as these two random variables are jointly normally distributed, they are independent. Subsequently, the following ratio that divides a standard normal variable by the square root of a chi-square distribution divided by its degrees of freedom, and both are independent, then this ratio, again, is distributed as a t distribution with n minus k degrees of freedom. Finally, remember that the t distribution converges to the normal distribution, and we are going to use this statistic usually to test the null hypothesis that beta t equals 0 against the alternative hypothesis that beta t is different from 0. In order to conclude, in this lecture we have revisited the fundamentals of OLF regression for the case of time series data in finite samples. We have shown under what condition the estimators are the minimum variance, linear and unbiased, blue, for the case of stochastic and non-stochastic regressors as well. It is imperative to check that these assumptions are met and eventually apply the corresponding corrective methods. If you are suspicious, for example, that the errors are related with the regressor or explanatory variables, just use instrumental variable methods or two-stage least square. If you have proof that the variance of the error in its content or the errors are autocorrelated, just change appropriately the variance-covariance matrix of the errors, or use generalized least square methods. As we have seen, almost everything is the same as in cross-sectional data, except for the case of strict exogeneity and autocorrelation of the errors, where the conditions are somewhat stricter. The coefficient of determination is similar to the one established in cross-sectional data, with some minor difference regarding the trend of the series. And remember, statistical significance of the coefficients does not compensate for a low R-square. Don't get trapped in the p-value hacking problem. As in the case of cross-sectional data, we have shown the probability distribution of the estimators in order to perform the typical hypothesis tests. As can be seen in other lectures, some of the assumptions can be relaxed as long as the number of observations is large enough. I want to thank you again very much for giving me the opportunity of teaching this lesson. I hope that you enjoy it as much as I did. Goodbye.